Welcome, curious minds, to What Is, where we tackle the biggest questions, one profound query at a time. Today, oh boy, today we're tackling the biggest. Not just big in scope, but big in sheer, mind-boggling, existential awe. Today we ask, what is the universe? Now, before you reach for your philosophical dictionary or that tinfoil hat, let's be clear. This isn't a simple question with a neat, tidy answer. It's a centuries-long epic of discovery, a cosmic detective story, and honestly, a testament to humanity's stubborn refusal to simply not wonder. So buckle up, because we're about to embark on a journey that spans billions of years, light years, and more than a few fundamental misunderstandings. We'll explore what our current understanding tells us, how we stumbled and soared through historical perspectives, and where we might be headed as we peer into the grand and enigmatic future of cosmic discovery. Prepare yourselves. Your tiny speck of existence is about to get a whole lot more interesting. 1. Current understanding. So what is the universe, according to our latest, greatest scientific understanding? At its most fundamental, the universe is everything, and I truly mean everything. All of space, all of time, all matter, all energy, and the very laws and constraints that govern them. It's a vast, accelerating expanse that began with an event we call the Big Bang, roughly 13.8 billion years ago. It's not just a collection of stars, it's a cosmic web of galaxies, each containing billions or even trillions of stars, planets, gas clouds, and dark, empty spaces. Our own galaxy, the Milky Way, is just one of an estimated 2 trillion galaxies observable from Earth. That's 2 trillion with a T. Let that sink in for a moment. If you tried to count them, dedicating 1 second to each, you'd be counting for over 63,000 years. You'd better pack a lunch. And these galaxies aren't just sitting still. They're rushing away from each other, carried along by the expansion of space itself. Think of it like the dots on an inflating balloon. The dots aren't moving on the surface between them is growing. This expansion, we now know, is actually accelerating, pushing along by something truly mysterious. Enter the cosmic dark side, dark matter and dark energy. Together, these two comprise about 95% of the universe. That's 95%. All the stars, planets, you, me, everything we can see, touch, or detect with our most powerful telescopes, that's just the visible 5%. It's like arriving at a massive party and realizing you only know about 5% of the guest. The other 95% are invisible, intangible, and incredibly influential. We can't see dark matter, but we know it's there because of its gravitational effects on galaxies. It's the unseen scaffolding that holds the galactic structures together. If you want to find out more, we have a video on dark matter specifically, which will be linked above. Then there's dark energy, the ultimate cosmic enigma. This is the stuff that's driving the accelerated expansion of the universe. It's like an anti-gravitational force pushing things apart. We have no idea what it is, where it came from, or why it exists, but it's the dominant energy density in the universe. It's the biggest mystery box in the cosmos, and we're just staring at it, desperately trying to pick the lock. Our current understanding also tells us about the very early universe, thanks in large part to the cosmic microwave background, or CMB. This faint glow of radiation, detectable across the entire sky, is essentially the afterglow of the Big Bang, the oldest light in the universe. It's a baby picture of the cosmos, taken when it was just 380,000 years old. Before that, the universe was too hot and dense for light to travel freely. It was a cosmic soup. The CMB gives us incredible clues about the universe's initial conditions, its composition, and how structure began to form. So the universe as we see it today is a vast, expanding, accelerating, dark matter-filled, dark energy dominated tapestry, born from a singular event and still ringing with the echoes of its infancy. It's elegant, it's intricate, and it's profoundly humbling. And the best part? We're only just beginning to truly grasp its incredible complexity. 2. Historical perspective, evolving ideas. But how did we get here? From staring at the stars with wide-eyed wonder to mapping the cosmic microwave background. It wasn't a straight path, let me tell you. It was more like a winding, often confusing, occasionally hilarious, but ultimately triumphant journey of evolving ideas. For most of human history, the universe was a much simpler, albeit more self-important, place. The prevailing view for thousands of years was that Earth was the center of everything. We were clearly special, right? The sun, the moon, the stars, all revolved around us. It made sense from a purely observational standpoint. Everything looks like it's orbiting Earth. The ancient Babylonians, for instance, saw the cosmos as a series of nested spheres, with Earth in the middle. The ancient Greeks, particularly figures like Ptolemy around the 2nd century AD, refined this geocentric model into a sophisticated system of epicycles and deferents to explain the seemingly erratic movements of planets. It was a mathematical marvel that worked surprisingly well for predicting planetary positions, even if it was fundamentally wrong about the cosmic address. It was like building an incredibly complex Rube Goldberg machine to make toast, when all you really needed was a toaster. But hey, it made sense to them, and it stuck around for over 1,400 years. Talk about stubborn. Then came the scientific revolution, and things started to get a little less self-centered. In the 16th century, a Polish astronomer named Nicholas Copernicus proposed the radical idea. Maybe the sun, not the Earth, was at the center of the solar system. The heliocentric model was born. It was simpler, more elegant, and explained planetary motion far better. But it was also controversial. It challenged the deep ingrained religious and philosophical beliefs. Enter Galileo Galilei in the early 17th century, who with his improved telescope provided observational evidence that supported Copernicus. He saw moons orbiting Jupiter, phases of Venus like those of our moon, and craters on the moon. These observations directly contradicted the idea of perfect celestial spheres orbiting Earth. His discoveries got him into a bit of trouble, to put it mildly. But the cosmic cat was out of the bag. Isaac Newton, later that century, then provided the mathematical framework for this new universe with his laws of motion and universal gravitation. Suddenly, the heavens and Earth were governed by the same set of predictable laws. Gravity explained why apples fell and why planets orbited. The universe was still finite, a sort of clockwork mechanism, but it was vast and governed by elegant principles. For a long time, our galaxy, the Milky Way, was thought to be the entire universe, until the early 20th century, that is. Turns out, we were still thinking a bit small. This brings us to the monumental contributions of Albert Einstein. In the early 1900s, his theories of special and general relativity revolutionized our understanding of space, time, gravity, and the universe itself. Gravity wasn't just a force, it was the curvature in the fabric of space-time caused by mass and energy. This opened up entirely new ways to think about the universe dynamically. Einstein himself initially added a cosmological constant to his equations to force the universe to be static, as this was the prevailing belief. He later called this his biggest blunder, when evidence for an expanding universe emerged. Even the super geniuses can make mistakes. And that evidence largely came from Edwin Hubble in the 1920s. Using powerful telescopes, Hubble observed distant nebulae, thought to be gas clouds within our galaxy, and realized they were actually other galaxies far, far away. He also noticed that the light from these galaxies was redshifted, meaning they were moving away from us, and the further away they were, the faster they were receding. This was the observational proof of an expanded universe. The idea of a static island universe was shattered. This expansion led to the development of the Big Bang theory. Georges Lemaitre, a Belgian priest and physicist, first proposed the idea of a primeval atom, or cosmic egg, that exploded. Later, George Gamow and his colleagues developed the theory further, predicting the existence of the cosmic microwave background radiation. And guess what? In 1964, Arno Penzias and Robert Wilson, while trying to troubleshoot a pesky noise in their antenna at Bell Labs, accidentally discovered this very CMB radiation. They thought it was just pigeon droppings or faulty equipment, but it was actually the faint, uniform glow from the universe's infancy. This serendipitous discovery provided powerful evidence for the Big Bang and marked a turning point in modern cosmology. We had found the cosmic baby picture. So in just a few thousand years, humanity's understanding of the universe evolved from an Earth-centered celestial sphere to the Sun-centered clockwork, then to a galaxy as universe model, and finally to the vast, expanding cosmos born from a hot, dense state. It's a tale of constant revision, challenging assumptions, and embracing the unexpected. It proves that our current understanding, while robust, is just another step in this incredible intellectual journey. 3. The future. Alright, so we've peeked into the past, celebrated the present, and now we must gaze into the future. What mysteries remain? What questions will future generations of scientists grapple with as they continue humanity's grand cosmic quest? The truth is, despite our incredible leaps in understanding, our knowledge of the universe is still remarkably incomplete. Remember that 95% of the universe composed of dark matter and dark energy? Yeah, that's our biggest blind spot. Understanding these enigmatic components is the holy grail of modern cosmology and particle physics. What are they? Are they new particles, modifications to gravity, or something even more bizarre that we haven't even conceived of yet? The future will bring new experiments, new detectors like the Large Hadron Collider, looking for dark matter particles, or next-generation observatories mapping the universe with unprecedented precision to understand dark energy's influence. Another profound question: what happened before the Big Bang? Or is before even a meaningful concept when time itself is thought to have begun with the Big Bang? This touches on theories like the cyclic universe, where our universe might just be one in an endless series of expansions and contractions, or the multiverse theory, which suggests our universe is merely one bubble in a foam of countless others. These are speculative, yes, but they represent the cutting edge of theoretical physics, pushing the boundaries of what we can even imagine. And of course, the age-old question that continues to captivate us all: are we alone? Is there life beyond Earth? With the discovery of thousands of exoplanets, planets orbiting other stars, the odds seem increasingly high. Future telescopes, like the James Webb Space Telescope, are already beginning to analyze the atmospheres of these distant worlds for biosignatures, chemical indicators of life. Imagine the day when we confirm microbial life on another planet, or even dare to dream, detect signals of intelligent civilizations. That would fundamentally alter our understanding of our place in the cosmos. Then there's the ultimate fate of the universe. What will happen in billions, trillions, or even quadrillions of years? Will it continue to expand indefinitely, eventually fizzing out in a heat death, where all the energy is evenly distributed and nothing more can happen? Will dark energy tear apart galaxies, stars, and even atoms in a big rip? Or, less likely given current data, will it reverse course and collapse back in on itself in a big crunch? Our understanding of dark energy will dictate our final cosmic chapter. The scientific tools of the future will be astonishing. We're building gravitational wave observatories like LIGO and soon LISA, which don't just see light, but hear the ripples in space-time caused by cataclysmic events like colliding black holes. This opens up an entirely new window into the universe, allowing us to observe phenomena that are invisible to traditional telescopes. We are developing AI and machine learning to sift through the unimaginable amounts of data we collect, finding patterns and anomalies that the human eyes might miss. The future of understanding the universe isn't about finding answers, it's about asking better questions. It's about building bigger, more sensitive instruments. It's about fostering collaboration across disciplines and cultures. It's about nurturing that fundamental human curiosity that has driven us from staring at campfires to launching telescopes into space. The universe is a story that's still being written, and we as a species are both eager readers and active participants. We are tiny beings on a small blue planet, yet we possess the capacity to ponder the infinite, to decode the cosmos, and to marvel at its profound beauty and complexity. And that, in itself, is perhaps the greatest wonder of all. So what is the universe? It's everything we know, everything we don't, and everything we've yet to imagine. It's a journey from ancient myths to quantum gravity, from geocentric certainty to cosmic humility. It's a testament to the power of human curiosity and our relentless pursuit of knowledge. From the visible matter of stars and planets, to the elusive dark matter and dark energy that dominate its fabric, from the fiery birth of the Big Bang to its uncertain future, the universe is a living, breathing, constantly evolving mystery, and we are incredibly fortunate to be here now to witness and participate in its unfolding story. Thank you for joining us on this incredible cosmic adventure. If this journey through space and time has left you with even more questions, or perhaps a renewed sense of awe, then we've done our job. Don't forget to like this video, subscribe to What Is for more deep dives into the perplexing, the profound, and the absolutely fascinating. And let us know in the comments, what aspects of the universe do you find most mind-blowing? We love to hear your thoughts. Until next time, keep looking up and keep asking what is, and keep exploring the boundless wonders of our amazing universe. See you next time. Hello and welcome back to What Is. Today we're diving headfirst into one of the most mind-bending, existential questions humanity has ever dared ask. A question that keeps astronomers up at night, fuels countless sci-fi plots, and has probably made you stare up at the night sky and wonder, with a slight shiver, where is everybody? We are talking, of course, about the Fermi Paradox. Now, before you picture some ancient alien being named Fermi, let's clear that up. The paradox isn't named after an alien, it's named after Enrico Fermi, a brilliant Italian-American physicist. The story goes that one lunchtime in 1950, while working at Los Alamos, Fermi and his colleagues were discussing a recent UFO sighting and the possibility of faster-than-light travel. One of his colleagues supposedly asked, "Do you ever wonder where everybody is?" And Fermi, with a shrug, simply replied, "But where is everybody?" And just like that, a casual lunch conversation birthed one of the most profound mysteries of the cosmos. So what exactly is the Fermi Paradox? In its simplest form, it's the stark contradiction between the high probability that intelligent extraterrestrial life exists and the utter lack of observable evidence to support it. Think about it. Our galaxy alone, the Milky Way, contains an estimated 100 to 400 billion stars. And the observable universe? We're talking about trillions of galaxies, each packing billions of stars. It's a truly astronomical number, pun absolutely intended. This isn't just a vague feeling. For decades, scientists have been trying to quantify the likelihood of life elsewhere. Enter the Drake equation. Dreamed up by astronomer Frank Drake in 1961, it's not meant to give a definitive answer, but rather organize our ignorance to get us thinking about the factors involved in the potential for communicating extraterrestrial civilizations in our galaxy. The Drake equation looks like this. N equals R star times F sub P times N sub E times F sub L times F sub I times F sub C times L. Yeah, it's a mouthful, but let's break it down in concept without getting lost in the math weeds. It starts with R star, the rate of star formation in our galaxy. Then F sub P, the fraction of those stars that have planets. Then N sub E, the average number of planets that can potentially support life per star that has planets. Then F sub L, the fraction of those life-supporting planets that actually develop life at some point. Then F sub I, the fraction of planets with life that go on to develop intelligent life. Followed by F sub C, the fraction of intelligent civilization that develop technology capable of sending detectable signals into space. And finally L, the length of time such civilizations release those detectable signals into space. If you plug in even conservative, dare I say pessimistic, estimates for each of these variables, the resulting N, the number of detectable civilizations in our galaxy, often still comes out to be a really big number, like hundreds, thousands, or even millions. And yet silence. Crickets. Not even a cosmic "you've got mail." The universe, according to our calculations, should be teeming with life, perhaps even advanced civilizations. Many of these civilizations, given the sheer age of the universe, nearly 14 billion years, should have a massive head start on us. Some of them could be billions of years older than Earth. Imagine what a civilization just a million years more advanced than us could achieve. They might have colonized entire galaxies, built Dyson spheres around their stars, or sent self-replicating probes across the cosmos. So where are they? No signs, no signals, no ancient alien megastructures photobombing our telescopes. That, my friends, is the Fermi Paradox in its full, baffling glory. It's the ultimate cosmic ghost town. Now humanity, bless its curious heart, isn't one to back down from a good paradox. Over the years, countless theories have popped up to try and answer Fermi's simple yet profound question. These theories generally fall into a few broad categories. Either they exist but we don't see them, or they don't exist, or they're extremely rare. Let's dive into some of the more popular and perhaps most unsettling explanations. One of the most chilling and widely discussed solution is something called the Great Filter. This idea suggests that at some point between the birth of a star and the emergence of multi-galaxy spanning civilization, there is an incredibly difficult, almost impossible step or series of steps that almost all life fails to pass. This filter could be behind us, or it could be terrifyingly ahead of us. If the Great Filter is behind us, it means something incredibly rare and improbable happened for us to get here. Maybe the jump from non-life to replicating simple life is the filter. We don't fully understand abiogenesis, how life first sparked from non-living matter. Perhaps that is the part that almost never happens. Or maybe the transition from simple prokaryotic cells to complex eukaryotic cells, with their tidy little organelles and nuclei, is the filter. That took billions of years on Earth, a huge evolutionary bottleneck. Or maybe it's the development of multicellularity, or intelligent life, or even the jump to tool-making and civilization. If any of these steps are the filter, then we won the cosmic lottery, and we might be alone or among the very first. That's a comforting thought in a sort of lonely way. But what if the Great Filter is ahead of us? This is where things get truly existentially terrifying. It would mean that some catastrophic event or self-destructive tendency inevitably wipes out advanced civilizations before they can expand into the galaxy. This could be anything from global warming, nuclear war, AI gone rogue, bioengineered plagues, asteroid impacts, or even exhausting the planet's resources. In this case, then every time we make a new technological leap, say developing self-replicating nanobots or mastering fusion power, we're not just celebrating progress, but potentially hurtling ourselves closer to the very filter that silenced everyone else. It implies that any civilization that reaches a certain level of achievement is doomed. And that silence out there? It's a graveyard. Makes you want to hug a space rock, doesn't it? Another set of theories falls under the umbrella of they exist, but we don't see them. One of the more famous is the zoo hypothesis. This posits that extraterrestrial civilizations are aware of us, but they have deliberately chosen not to contact us. We're like a protected species in a cosmic nature preserve, observed from afar but not interacted with, perhaps until we reach a certain level of technological or societal maturity. They're watching us with popcorn, cheering us on, or maybe just shaking their heads, waiting for us to figure out how to stop arguing over silly things. The universe as one giant, slightly condescending reality show. A variation of this is the planetarium hypothesis, suggesting that the universe we perceive is actually a simulated reality, engineered by an advanced civilization. Everything we see, the stars, the galaxies, the emptiness, is just part of a sophisticated projection painstakingly created to make us believe we're alone in the universe. Like a very convincing VR experience. This one really messes with your head, right? Is it even real? Am I real? Are you real? Probably best not to dwell on that one too much before bedtime. Then there's the simpler explanation. Maybe we're just looking in the wrong way or in the wrong place. Our search for extraterrestrial intelligence, or SETI, has largely focused on radio waves, listening for signals that resemble deliberate broadcasts. But what if advanced civilizations use completely different methods of communication? Perhaps they communicate using neutrinos, or gravitational waves, or quantum entanglement, or something we haven't even conceived of yet. Maybe our radio telescopes are like trying to find a high-speed internet connection with an old telegraph. Perhaps they've moved beyond broadcasting altogether, preferring quieter, more efficient methods of information transfer. Distance and time are also massive factors. The universe is unbelievably vast. Even if there are civilizations out there, they could be so far away that their signals haven't reached us yet, or they're too faint to detect. Light, as fast as it is, still takes thousands, millions, even billions of years to travel across the cosmos. We might only be receiving signals from civilizations that are long dead, or sending signals that won't be received until long after we're gone. It's like trying to have a conversation with someone on the other side of the planet, but your message takes 1,000 years to get there. By the time they reply, you've completely forgotten what you asked. What if they've transcended their physical form entirely? This theory suggests that highly advanced civilizations might evolve beyond biological bodies, perhaps uploading their consciousness into supercomputers or transforming into pure energy. If so, they wouldn't be building giant megastructures or sending out radio signals. They'd be living an entirely different mode of existence, perhaps undetectable by our current methods. They're just chilling in the cosmic cloud, probably judging our primitive meat suits. Then we have what some call the dark forest hypothesis, proposed by the Chinese science fiction author Liu Cixin in his novel The Dark Forest. This is a truly grim prospect. It suggests that the universe is a dark forest, and every civilization is a hunter. Contacting another civilization is incredibly risky, because you don't know if they're friendly or hostile. Therefore, the safest strategy is silence. And if you detect another civilization, the most logical course of action is to destroy them before they can destroy you. It's a cosmic game of hide and seek where the stakes are annihilation. In this scenario, the silence isn't empty, it's terrifyingly deliberate. Now let's explore the other main category of answers. They don't exist, or they're extremely rare. This brings us back to the Great Filter, but from a different perspective, one where we are the exception rather than the rule. The rare Earth hypothesis argues that the specific conditions on Earth that allow for the evolution of complex life are incredibly rare, perhaps unique. It's not just about the planet being in the Goldilocks zone, not too hot, not too cold, but a whole host of other factors. We have a large moon stabilizing our axial tilt, ensuring relatively stable seasons. We have Jupiter acting as a cosmic vacuum cleaner, deflecting dangerous asteroids. We have plate tectonics, recycling nutrients and regulating our climate. We have a protective magnetic field, getting all of these planetary features just right, in the right kind of star system, in the right part of the galaxy, at the right time in the universe's history. It might be an astronomically low probability event, so life might be common, but complex, intelligent life, that's the real cosmic unicorn. A related idea is that life itself might be common, but the jump to intelligent, and especially technological life, is what's rare. Think about Earth. Life appeared relatively early, within 1 billion years of the planet forming. It took another 3.5 billion years for anything resembling intelligence to evolve, and only a tiny fraction of species ever developed the kind of technology we possess. Dinosaurs ruled for 150 million years and never once built a radio telescope. Maybe intelligence isn't an inevitable evolutionary outcome, but a rare quirk, a side branch on the tree of life. So with all these theories swirling around, what exactly are we doing to answer Fermi's question? Well, we haven't given up hope. The search for extraterrestrial intelligence, or SETI, is still very much active. Projects like the Allen Telescope Array in California are constantly scanning the skies, listening for any artificial signals. While primarily focused on the radio frequencies, there are also efforts in optical SETI, looking for brief, powerful flashes of light that could be intentional laser communications. It's a painstaking process, sifting through mountains of data, but the hope of detecting even a faint whisper from another civilization keeps the lights on. We've also done a bit of shouting into the void ourselves. The Voyager and Pioneer probes, launched decades ago and now streaking out beyond our solar system, carry golden records and plaques, messages in a bottle if you will, containing sounds, images and diagrams of life on Earth, intended for any extraterrestrial civilization that might intercept them. It's our cosmic business card, hoping someone finds it and gives us a call. Perhaps our most promising avenue of discovery lies in exoplanet research. Missions like the Kepler Space Telescope and now the Transiting Exoplanet Survey Satellite, or TESS, have revolutionized our understanding of planets outside our solar system. We have gone from speculating about other worlds to confirming thousands of them, many in the habitable zones of their stars. This data helps us refine the Drake equation parameters and identify promising targets for further investigation. And the next generation of telescopes like the James Webb Space Telescope, or JWST, is pushing the boundaries even further. While it can't directly image alien cities, it can analyze the atmospheres of exoplanets, looking for biosignatures, chemical compositions that might indicate the presence of life, things like oxygen, methane, or even unusual combinations of gases that would be difficult to explain without biological processes. It's like sniffing for clues from billions of miles away. There's also the Breakthrough Listen project, a massive, privately funded initiative that's conducting the most comprehensive search for alien communications ever undertaken. Imagine scanning 1 million nearby stars, 100 nearby galaxies, and even the galactic plane for unusual radio and optical signals. They're essentially casting a much, much wider net. Ultimately, the Fermi Paradox remains unsolved. We continue to search, to listen, to probe, driven by that intrinsic human curiosity to understand our place in the universe. Are we alone? Are we one of many? Are we a cosmic anomaly? a miracle against all odds? Or are we simply living in a quiet neighborhood of a very, very big city, just waiting for someone to finally throw a party? The silence is profound, but it's also a canvas for our imagination, a challenge to our scientific ingenuity, and a constant reminder of the incredible mysteries that still lie beyond our grasp. It forces us to confront our own potential, our own fragility, and our own destiny. So the next time you look up at the stars, instead of seeing just twinkling lights, remember the deeper questions they pose. And remember the answer, whatever it may be, will redefine humanity's understanding of itself forever. Thank you for joining us on this mind-bending journey through the Fermi Paradox. If you enjoyed this cosmic deep dive, please give this video a big thumbs up, share it with your fellow stargazers, and don't forget to subscribe to What Is for more episodes that unravel the universe's biggest and smallest questions. Hit that notification bell too, so you never miss another journey into the unknown. We love hearing your thoughts, so tell us in the comments below, what is your favorite theory for solving the Fermi Paradox, and where do you think everyone is? Until next time, keep looking up. Imagine, if you will, that you're trying to build a universe. You've got your blueprints, you've got your fundamental forces, and you've got a handful of subatomic particles like electrons and quarks. You put them all together, step back to admire your work, and then whoosh, everything flies apart at the speed of light. Your stars won't form, your planets won't stick, and you certainly don't exist to complain about it. Why? Because in your beautiful new universe, nothing has weight, nothing has mass. Everything is just zipping around like a caffeinated toddler in a bouncy castle. Welcome to What Is, and today we're diving into the subatomic mystery that explains why we aren't all just light-speed ghosts. We're talking about the Higgs Boson, the so-called God particle, the most expensive secret in history, and the reason you actually have a shape. Before we smash some protons together, make sure to hit that subscribe button and ring the bell so you never miss a deep dive into the what is of our reality. To understand the Higgs, we have to travel back to the early 1960s. Physics was having a bit of a midlife crisis. Scientists had developed something called the Standard Model. It was a tidy little list of all the particles that make up the universe. It was elegant. It worked perfectly. Except for one tiny, glaring, universe-breaking problem. The math said that all these particles should be massless. Now in physics, massless doesn't mean light. It means that you have no choice but to travel at the speed of light. Forever. If an electron has no mass, it can't orbit a nucleus to form an atom. If there are no atoms, there's no chemistry. No chemistry, no coffee. No coffee, no civilization. The physicists were stuck. Their math was beautiful, but it described a universe that didn't look like ours. Enter Peter Higgs, a soft-spoken British theorist, along with Francois Englert, Robert Brout, and a few others. In 1964, they proposed a radical idea. What if the entire universe is filled with an invisible field? A sort of cosmic molasses that sticks to everything? They called it the Higgs field. The idea was that particles don't just have mass as an intrinsic property. Instead, they gain mass by interacting with this field. Think of it like this. Imagine a crowded room at a Hollywood party. The room itself is the Higgs field. Now imagine a nobody, say me, walked into the room. Nobody knows me. I can zip through the crowd at top speed because no one stops to talk to me. I have very little mass in that environment. But now imagine Beyoncé walks into the room. Everyone crowds around her. They want autographs, selfies, a moment of her time. She can barely move. The field of people sticks to her, slowing her down. To the room, she effectively has a lot of mass. In this analogy, an electron is a minor celebrity, and the top quark, the heaviest known particle, is basically the Beatles in 1964. And a photon is the guy who's just there to fix the AC. He moves right through the crowd, totally ignored at the speed of light. But here was the catch. If this field existed, there had to be a way to prove it. According to the rules of quantum mechanics, every field has a corresponding particle. If you jiggle the field hard enough, a particle should pop out. That particle was the Higgs boson. For 40 years, it remained just a ghost on the chalkboard. And maybe it was the missing puzzle piece of the universe, and without it, the whole picture of physics stayed blurry. By the 1980s and 90s, the hunt was on. But finding a Higgs boson isn't like finding a needle in a haystack. It's like finding a specific piece of hay that only exists for a billionth of a second inside a haystack that's currently exploding. To find it, we needed the biggest, most complex machine humanity had ever built. We needed the Large Hadron Collider, or the LHC. Built by CERN, the LHC is a 27-kilometer ring of superconducting magnets buried 100 meters under the border of France and Switzerland. It is, quite literally, the world's most expensive and high-stakes demolition derby. The plan was simple in theory, but terrifying in practice. Take two beams of protons, accelerate them to 99.99999999% the speed of light in opposite directions, and smash them into each other. The energy released in these collisions is meant to mimic the conditions of the universe just a fraction of a second after the Big Bang. At those energy levels, the Higgs field might just get jiggled enough to spit out a Higgs boson. But before the machine even got turned on, the world got a little nervous. You might remember the headlines from 2008. There were lawsuits. There were claims that the LHC would create a microscopic black hole that would swallow the Earth. Spoiler alert, it didn't. We're still here, mostly. The LHC was a triumph of engineering. It operated at temperatures colder than outer space, while the collisions created heat 100,000 times hotter than the center of the sun. It produces so much data that if you burned it all to CDs, the stack would reach the moon. For years, the scientists at CERN watched the data. They weren't looking for a flash or a bang. They were looking for a bump in the graph, a tiny deviation that suggested a particle with a specific mass was decaying into other particles in a way that nothing else could. The tension was insane. Every time the machine broke down, once due to a bird dropping a piece of baguette into an outdoor power substation, which is the most French way to delay the apocalypse ever, the world waited. Then came July 4th, 2012. Physicists from across the globe gathered in a lecture hall at CERN. Peter Higgs, then 83 years old, sat in the front row. The spokespeople for the two main experiments, CMS and Atlas, stood up to present their findings. They both showed the same thing, a bump. Right there at the 125 gigaelectron volt mark, they announced they had reached a 5 sigma level of certainty. In human terms, that means there's only 1 in 3.5 million chance that what they were seeing was a fluke. The room erupted. Peter Higgs pulled out a handkerchief and wiped his eyes. "It is an incredible thing that it has happened in my lifetime," he said. It was one of the greatest scientific achievements in human history. We had found the soul of mass. So, what does this mean for you, sitting there watching this video? First, it means the standard model is mostly correct. We finally understand why matter has substance. Without the Higgs boson, the atoms in your body would have no mass, and you would dissolve in a burst of radiation traveling at the speed of light. So, thank a boson for your existence today. Second, let's address the God particle thing. Leon Lederman, a Nobel Prize-winning physicist, coined the term in a book title. Scientists generally hate it. Lederman actually wanted to call it the goddamn particle, because it was so hard to find, but his publisher wouldn't let him. So God particle it was. It doesn't prove anything about religion. It just proves that marketing is a powerful force of nature. But the discovery of the Higgs isn't the end of the story. In many ways, it's just a very expensive chapter 1. The Higgs boson we found is actually kind of weird. It's a little bit too light. In physics, being too light is a red flag. It suggests that there might be other particles out there, supersymmetric particles, that we haven't seen yet. Even crazier is the theory of vacuum decay. Some calculations suggest that the Higgs field might not be at its most stable state. It might be in what's called a metastable state. Imagine a ball sitting in a slight dip on the side of a mountain. It's stable for now, but if you give it a big enough poke, it could roll down to the very bottom of the valley. If our Higgs field rolls down to a lower energy state, it would create a bubble of new physics that would expand at the speed of light, incinerating everything in the universe and rewriting the laws of reality as it goes. There's no need to panic. The math says this won't likely happen for another 10 to the power of 100 years. You still have time to pay your taxes. Looking to the future, CERN is already planning for the Future Circular Collider, a machine 4 times bigger and significantly more powerful than the LHC. Why? Because the Higgs boson might be the portal to understanding dark matter. Dark matter makes up about 85% of the matter in the universe, but we can't see it, touch it, or detect it with normal instruments. But the Higgs boson interacts with mass, and dark matter has a lot of mass. The Higgs might be the bridge between the world we know and the dark universe we don't. We spent 50 years and billions of dollars trying to find one tiny flicker in a vacuum. Was it worth it? When people asked Robert Wilson, the first director of Fermilab, if the massive particle accelerator would help national defense, he said, "It has nothing to do directly with defending our country, except to help make it worth defending." The Higgs boson is a testament to human curiosity. We are a bunch of apes on a wet rock who decided we wanted to know why things are heavy. And then we built a 27-kilometer subterranean ring to find out. We found the grain of sand that gives the universe its weight. Now we just have to figure out what the rest of the beach looks like. If you enjoyed this journey into the subatomic, give this video a like and let us know in the comments what is one scientific mystery that keeps you up at night. Is it dark matter? Is it vacuum decay? Honestly, that one is starting to get to me. Thank you for watching What Is. Don't forget to subscribe for more deep dives into the big questions, all the small stuff, and the big stuff, and everything in between. We'll see you in the next one. Welcome to What Is. Today we're diving into a topic that makes most people's brains feel like they've been dropped into a blender and set to puree. It's the bedrock of modern physics, the bane of Albert Einstein's existence, and the reason why, at the most fundamental level, the universe is a giant cosmic game of I don't know maybe. We're talking about the Heisenberg Uncertainty Principle. Now before you click away because you saw the word physics, let me promise you 2 things. 1, there will be no surprise midterm exams. 2, by the end of this, you will understand why the very fabric of reality is surprisingly blurry. But before we get to the blur, we have to go back to a time when everyone thought they had the universe figured out. A time when the universe was considered a giant, predictable clock. To understand the uncertainty principle, we have to first understand the man who broke the clock, Werner Heisenberg. Part 1, Origins, the Hay Fever Revolution. In the early 1920s, physics was in a bit of a midlife crisis. For centuries, Sir Isaac Newton reigned supreme. His laws of motion were perfect. If you knew where a ball was and how fast it was moving, you could predict exactly where it would be in 10 seconds, 10 years, or 10 centuries. It was the era of determinism. The universe was a machine, and if you had a big enough calculator, You could map out the entire future. Then came the atom. Scientists like Niels Bohr had proposed a model where electrons orbited the nucleus like planets around the sun. It was neat, it was tidy, it was also wrong. The deeper physicists looked, the more the clockwork universe started to rattle and smoke. Electrons weren't behaving like planets. They were jumping around, disappearing and reappearing, and acting like they'd had way too much espresso. Enter Werner Heisenberg. In 1925, Heisenberg was a 23-year-old German physicist with a massive brain and an even more massive case of hay fever. His allergies had gotten so bad that his face swelled up until he looked like he'd gone 10 rounds with a heavyweight boxer. To escape the pollen of Gothenburg, he fled to a desolate, treeless island in the North Sea called Heligoland. There, alone on a rock in the middle of the ocean, with nothing but the wind and his own sneezing, Heisenberg did something radical. He decided to throw away everything we thought we knew about atoms. He said, if we can't see the electrons orbiting like planets, let's stop pretending they do. Let's only work with what we can actually observe. He spent the nights climbing rocks and the days doing maths so complex it hadn't even been fully integrated into physics yet. He was inventing what we now call matrix mechanics. When he finally crunched the numbers, he realized that the math worked, but it had a very strange quirk. In normal math, 2 times 3 is the same as 3 times 2. In Heisenberg's math, the order mattered. If you multiplied position by momentum, you got a different answer than if you multiplied momentum by position. At first, he thought this was a mistake. How could the order of multiplication change the result? But as he recovered from his hay fever and returned to the mainland, he realized it wasn't a mathematical error. It was a hint. Nature was trying to tell him that there is a limit to what we can know. Part 2. Development, the microscope of doom. Heisenberg, teaming up with his mentor Niels Bohr and his friend Max Born, were trying to make sense of this non-commutative math. By 1927, Heisenberg hit upon the core realization. He imagined a thought experiment. Suppose you want to measure the position of an electron. To see it, you have to bounce something off it, like a photon, a particle of light. Now imagine the electron is a tiny glass marble on a table. To see where it is, you shine a flashlight on it. In our everyday world, the light hits the marble and bounces back to your eye. The marble doesn't move because the light is too weak to push it. But an electron is unimaginably small. To see it clearly, you need a light with a very high frequency, like a gamma ray. The problem is, a gamma ray carries a lot of energy. The moment that light hits the electron so you can see where it is, it kicks the electron like a pro football player kicking a ball. So the act of measuring the electron's position gives it a massive, unpredictable shove, changing its momentum. If you use a softer light to avoid kicking it, the wavelength is too long and you can't get a clear picture of its position. You can know how fast it's going, the momentum, but you have no idea where it is. Heisenberg realized this wasn't a problem with our technology. It wasn't that our microscopes weren't good enough. It was a fundamental trade-off. The more precisely that you know the position of a particle, the less precisely you can know its momentum, and vice versa. He put this into a deceptively simple formula. Delta x, delta p is greater than or equal to h over 4 pi. Don't worry, there won't be a quiz on the symbols. Just know that x is position, p is momentum, and h is Planck's constant. The greater than or equal to sign is the key. It says that there's a minimum amount of fuzziness that you can never ever get rid of. It's the universe's way of saying, mind your own business. Part 3, Meaning, the Great Misconception. Now here is where we need to clear something up. People often confuse the Heisenberg Uncertainty Principle with something called the observer effect. The observer effect is the idea that the act of observing a system changes it. Like taking the pressure of a car tire, you have to let out a little air to get a reading, which changes the pressure. That's a common sense physical interaction. But the uncertainty principle goes much deeper. It's not just that we disturb the particle by looking at it, it's that the particle doesn't even have a definite position and momentum at the same time. Think about a wave in the ocean. If I ask you, where is the wave? You'd point to a general area. But a wave is spread out. It doesn't have a single point position. However, a wave does have a wavelength, which tells you something about its energy and motion. Now, if you take that wave and squeeze it until it's just a single sharp spike, a single point, you've defined its position. But in doing so, you've destroyed the wavelength. You no longer know its frequency or its motion. In the quantum world, particles are also waves. This is called wave-particle duality. Because an electron is a wave-like thing, it inherently lacks a perfectly defined location and speed simultaneously. The uncertainty principle isn't a limit of our knowledge. It's a property of reality. The universe is fundamentally blurry. It looks like a pointillist painting. From far enough away, everything looks sharp, but the closer you get, the more you realize it's just a bunch of dots with space in between. Heisenberg showed us that if you zoom in far enough on the universe, the image never gets sharp. It stays pixelated. This sends a shudder down the spine of classical logic. It means at the most basic level, the universe is not made of things with locations. It's made of probabilities. Part 4. Importance. The death of the clockwork universe. Why does this matter? Why did it make Albert Einstein so angry he spent the rest of his life trying to prove Heisenberg wrong? Well, because it kills the idea of total predictability. In Newton's universe, if you knew the position and the velocity of every atom in a person's body, you could, in theory, predict exactly what they would do next Tuesday at 4:13 p.m. There was no room for chance. There was no room for true randomness. Everything was a consequence of what came before. Heisenberg's principle says no. Since we can never know the exact present state of the universe, because we can't know both position and momentum, we can never accurately predict the future. Not just because we're not smart enough, but because the information literally does not exist. Einstein famously responded to this by saying, "God does not play dice with the universe." To which Niels Bohr reportedly replied, "Einstein, stop telling God what to do." The uncertainty principle shifted the goal of physics. We stopped trying to predict exactly what will happen and started calculating the probability of what might happen. This birthed the Copenhagen interpretation of quantum mechanics, which remains the standard, though darkly mysterious, way to understand the subatomic world today. It also introduced the concept of quantum fluctuations. If you have a tiny enough region of space and a tiny enough window of time, the uncertainty principle says that the energy can fluctuate wildly. In fact, empty space isn't actually empty. It's a bubbling cauldron of energy where particles pop in and out of existence, all because the universe isn't quite sure how much energy is supposed to be there at any given microsecond. Without uncertainty, the universe as we know it could not exist. There would be no stars, no planets, and definitely no humans. Part 5. Implications and further development. The tech in your reception. So is this all just philosophical navel-gazing? Does it affect your actual life, or is it just something physicists talk about to feel important at parties? Actually, you're using the Heisenberg Uncertainty Principle right now. Consider the transistor. It's a tiny switch inside your smartphone and computer. There are billions of them on a single chip. They work by controlling the flow of electrons. As we make transistors smaller and smaller, we run into a problem: quantum tunneling. Quantum tunneling is the direct result of the uncertainty principle. If an electron is approaching a barrier, its position is blurry. There's a small but real probability that its position is actually on the other side of the barrier. It tunnels through a wall that should be solid. Engineers have to account for this uncertainty to make your iPhone work. If they didn't understand Heisenberg's math, the electrons would leak out the circuits like water through a sieve, and your phone would be nothing more than an expensive glass-covered brick. Then there's the MRI machine. Magnetic resonance imaging relies on the behavior of atoms in a magnetic field. The precision which we can map your internal organs is limited by, and fundamentally described by, quantum mechanics and its inherent uncertainties. And it goes even bigger than that. Let's talk about the Big Bang. Modern cosmology suggests that the entire universe began as a tiny subatomic speck. In that state, the uncertainty principle reigns supreme. The massive structures we see today, galaxies, clusters of stars, are actually the result of quantum fluctuations from the beginning of time. These tiny ripples of uncertainty were stretched by the expansion of the universe into giant clouds of gas that eventually collapsed into stars. We are literally the children of cosmic blurriness. If the universe had been perfectly certain and ordered at the start, there would be no clumps. No clumps means no stars. No stars mean no planets. No planets mean no life. No life means no What Is YouTube channel. It would just be a very boring, perfectly smooth soup of hydrogen. Furthermore, Heisenberg's work paved the way for quantum electrodynamics, or QED, and the standard model of particle physics. It led to the discovery of antimatter. It led to Stephen Hawking's theory of Hawking radiation, which suggests that black holes aren't completely black, but leak radiation because of, well, you've guessed it, quantum uncertainty at the event horizon. The development continued through the 20th century, leading us to quantum entanglement, what Einstein called spooky action at a distance. While Heisenberg dealt with the uncertainty of a single particle, entanglement shows us that two particles can have their uncertainties linked, no matter how far apart they are. We are currently in the middle of a second quantum revolution. We are building quantum computers that don't use bits, ones or zeros, but qubits, which exist in a state of uncertainty until they are measured. These computers have the potential to solve problems in seconds that would take our current best supercomputers millions of years. All of this because Werner Heisenberg had a bad case of hay fever on a rocky island and realized that not knowing was the most important thing of all. Part 6. Embracing the Blur. The Heisenberg Uncertainty Principle is more than just a math equation. It's a perspective shift. It tells us that the universe is not a rigid cold machine. It's a place of potential. It's a place where, at the very deepest level, there's always room for the unexpected. It humbles us. It shows us that there are hard limits to human knowledge. We often think that as science progresses, we will eventually know everything. We will have the theory of everything. But Heisenberg shows us that the everything itself is built on a foundation of maybe. The uncertainty principle teaches us that precision isn't always the goal. On a human level, we often struggle with uncertainty. We want to know exactly what's going to happen tomorrow. We want to know exactly where we stand. But nature tells us that a little bit of blurriness is necessary for complex, beautiful things to happen. If everything was perfectly certain, everything would be static. It's the wobble in the atoms that allows chemistry to happen. It's the wiggle in the quantum fields that creates matter. So next time you feel like your life is a little chaotic, or you're not sure where you're going, just remember, that's how the universe likes it. Even the atoms you're made of aren't quite sure where they are. They've been doing just fine for 13.8 billion years. Heisenberg once said, "The first gulp from the glass of natural sciences will turn you into an atheist, but at the bottom of the glass, God is waiting for you." Whether you find God or just more math at the bottom of that glass, one thing is for sure, it's going to be a bit out of focus. Thank you for joining us on this deep dive into the wonderful fuzzy heart of reality. If you enjoyed this exploration of Heisenberg's uncertainty principle, make sure to hit that like button, or at least have a high probability of hitting it. What other what is questions are keeping you up at night? Let us know in the comments below. Don't forget to subscribe and ring the bell so you never miss an episode. This is What Is, and we'll see you in the next one. Probably. Actually, definitely. Well, within a certain margin of error. See you soon. Hello and welcome back to What Is, where we dive headfirst into the fascinating, the complex, and sometimes the downright mind-bending concepts that shape our world. Today we're not just talking about a theory, we're talking about a phenomenon that has inspired countless movies, freaked out meteorologists, and probably made you second guess whether to hit snooze this morning. We are, of course, talking about the one, the only, the legendary butterfly effect. You've heard the phrase, right? A butterfly flaps its wings in Brazil, and it causes a tornado in Texas. It sounds poetic. It sounds dramatic. But what is it really? Is it just a cool movie trope, or is there actually some science lurking behind the poetry? And perhaps more importantly, is it real? Stick around because we're going to untangle the science, the fiction, and the hilarious mishaps that a tiny flutter might, or might not, cause. What it is. At its core, the butterfly effect is all about something scientists call sensitive dependence on initial conditions. Now, don't let that jargon scare you off. It simply means that within a chaotic system, a very small change in the beginning can lead to a vastly different outcome later on. And we'll get to what chaotic really means in a minute. We're talking about a chain reaction where the tiniest tweak can send ripples through the entire system, growing exponentially until the end result is completely unrecognizable from what it might have been. Think of it like this. Imagine you're playing billiards. You line up your shot perfectly, aiming for the 8-ball. As you strike, a microscopic piece of dust on the table slightly defects the cue ball. We're talking about nanometers here, something you couldn't even see. That tiny, almost imperceivable deviation, compounded by all the subsequent collisions, means the balls don't go where you intended. The 8-ball misses the pocket, the cue ball bounces off 3 cushions, and suddenly your perfectly planned shot is a total mess. The butterfly effect isn't about direct causation in a linear sense. It's not saying this flap causes that tornado. It's saying that the flap, or any other tiny, seemingly insignificant disturbance, represents a change in the initial conditions of a massively complex, interconnected system. And when that system is chaotic, even the most minute alteration can steer it down an entirely different path. The key here is unpredictability. We're not talking about predicting that a specific flap will cause a specific hurricane. We're talking about the inherent inability to predict the long-term future of a chaotic system because you can never know its initial state with absolute perfect precision. There's always some tiny bit of information missing, some microscopic variable you haven't accounted for. And that missing piece? That's where the butterfly's wings, or the speck of dust, come in. They represent that initial, immeasurable nudge that can send everything spiraling off into a completely different future. It's both fascinating and, if you're a control freak, a little bit terrifying. Because it implies that perfect prediction, even with all the supercomputers in the world, might just be fundamentally impossible for certain types of systems. But hey, it keeps things interesting, right? Development. So where did this idea come from? Was it a philosopher pondering the cosmic dance, or a poet lost in thought? Nope. It came from a meteorologist, a brilliant scientist named Edward Lorenz, back in the early 1960s. And the story of its discovery is, ironically, a perfect example of the effect itself. Lorenz was a professor at MIT working on atmospheric modeling. He was trying to predict the weather, a notoriously tricky business. He developed a set of 12 nonlinear equations to simulate weather patterns on an early computer. One day in 1961, he decided to rerun the simulation to examine a specific sequence of weather in more detail. To save time, instead of starting the entire sequence from scratch, he entered the numbers from an earlier printout about halfway through the simulation. Here's where the magic happens, or rather, the chaos. The original program stored numbers with 6 decimal places, like 0.506127, but his printouts, to save space, truncated these numbers to 3 decimal places, like 0.506. Lorenz, thinking this tiny, almost imperceivable rounding difference wouldn't matter, confidently typed in the shorter numbers and went away to grab a cup of coffee, expecting to see a very similar weather pattern emerge when he returned. When he did return, much to his astonishment, the new weather pattern had completely diverged from the original. At first, the 2 simulations looked identical. Then, as time progressed in the model, they started to drift apart, slowly, subtly, until after a few simulated months, they bore absolutely no resemblance to each other whatsoever. The slight difference in the initial data, those 3 missing decimal places, had created a totally new weather forecast. This wasn't a bug. This was a revelation. Lorenz realized that even the smallest, most insignificant changes in the initial conditions could lead to drastically different long-term outcomes in complex systems like the atmosphere. He published his findings in a groundbreaking paper titled Deterministic Non-Periodic Flow in 1963, essentially founding the field of chaos theory. And later, while preparing a presentation for the American Association for the Advancement of Science, he coined that now famous phrase, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" And just like that, a scientific principle was born, named after a whimsical metaphor that perfectly captured its profound implications. Lorenz's work showed us that the world isn't always a predictable, clockwork mechanism. Sometimes it's a wonderfully, terrifyingly chaotic dance where even a whisper can start an avalanche. Use in pop culture. It didn't take long for such a compelling and dramatic concept to flutter its way out of scientific journals and into the heart of popular culture. The butterfly effect just sounds cinematic, doesn't it? It's a goldmine for storytelling, exploring themes of destiny, choice, and the terrifying power of even the smallest actions. Perhaps one of the most famous early nods came from the king of chaos himself, Jeff Goldblum, as Dr. Ian Malcolm in the original Jurassic Park. He famously demonstrated chaos theory by dropping water onto his hand, showing how a tiny change in the initial drip leads to an unpredictable path of the water. He then warns against the unpredictable nature of an island full of genetically engineered dinosaurs, famously proclaiming, "Life finds a way, and boy, did it ever find a way to eat people." Then there's the movie that literally bears the name, 2004's The Butterfly Effect, starring Ashton Kutcher. Here the concept is taken to its most extreme and literal interpretation. Kutcher's character has the ability to travel back in time to pivotal moments in his past and change a single, seemingly minor decision. Every alteration, no matter how small or well-intentioned, catastrophically rewrites his present, often leading to far worse, darker realities. It's a fascinating, if grim, exploration of the idea that some things are maybe best left alone, and that trying to control chaos can sometimes just make it angrier. But the idea predates a direct movie title. Think about films like Run, Lola, Run from Germany. We see 3 different scenarios play out for the protagonist Lola as she races against the clock to save her boyfriend. Each scenario is triggered by the most minor of initial differences: a slightly different pace, a misconnection, a split-second decision, each leading to wildly diverging conclusions. It's a masterclass in demonstrating how a fraction of a second can completely alter a person's fate. The film Sliding Doors explores parallel realities stemming from a tiny moment. Does Gwyneth Paltrow's character catch her train or miss it? That one instant splinters her life into 2 distinct timelines, each with different relationships, careers, and consequences. The film beautifully illustrates how seemingly inconsequential events can fundamentally reshape an entire existence. Even in television, shows like Lost played with elements of this, particularly with the Dharma Initiative's attempt to correct or alter events, only to often find themselves creating the very outcomes they were trying to prevent. It's the inherent irony of the butterfly effect. The more you try and control the chaotic system, the more you might inadvertently contribute to its unpredictability. Pop culture loves the butterfly effect because it taps into a fundamental human anxiety and wonder. Do my choices matter? How much impact do I really have? And what if that tiny thing I did or didn't do changed everything? It's a powerful narrative tool, reminding us that sometimes the smallest flutter can indeed feel like a seismic shift. Real-world implications. So the butterfly effect is great for a good movie plot, but does it actually, matter in the real world outside of a professor's computer simulation? Absolutely. The implications of sensitive dependence on initial conditions ripple through countless aspects of our lives, from the grand scale of global systems to the minutiae of our daily routines. Let's start where it all began: weather forecasting. This is perhaps the most direct and impactful real-world application. Edward Lorenz's discovery fundamentally changed how meteorologists approach their work. It explained why long-range forecasts are so incredibly unreliable. Even with the most sophisticated supercomputers and vast networks of sensors, we still can never measure the atmosphere's precise state down to every last molecule, every microscopic air current, every infinitesimal temperature fluctuation. Those tiny unmeasured variables are the butterflies, and their cumulative effect means that beyond about 7 to 10 days, weather predictions become highly speculative, if not outright educated guesses. It's not that the models are bad, it's that the system itself is inherently chaotic. Consider climate change. This is a macro-scale example, where seemingly small human actions like releasing greenhouse gases into the atmosphere over decades have triggered massive, complex, and unpredictable changes in global systems. A fraction of a degree increase in global temperature might seem insignificant, but its effect on ice caps, ocean currents, weather patterns, and ecosystems is profound and far-reaching, demonstrating a terrifying large-scale butterfly effect in action. Economics and financial markets are another prime example. They are incredibly complex, interconnected, chaotic systems driven by countless individual decisions, algorithms, and unforeseen events. A seemingly minor piece of news, a shift in investor sentiment, a small policy change, or even a single rogue trade can trigger a cascade of reactions that lead to market volatility, recessions, or even global financial crises. The 2008 financial crisis, for instance, involved the complex interplay of seemingly minor decisions and risk factors that spiraled into a global catastrophe. In ecology and biology, the introduction of an invasive species or the removal of a single keystone species from an ecosystem can have devastating and unpredictable ripple effects throughout the entire food web and habitat. Who knew that a few dozen zebra mussels brought over in ship ballast could wreak such havoc on an entire freshwater ecosystem? It's a slow-motion butterfly effect playing out over years and decades. Even in our personal lives, the concept resonates. Think about those what-if moments. What if I hadn't taken that specific job? What if I turned left instead of right? What if I'd responded to that email 5 minutes earlier? Small decisions, chance encounters, or even just being in the right or wrong place at the right time can alter the entire trajectory of our careers, relationships, and even our entire lives. Sometimes the butterfly flapping its wings is you, deciding on what to wear this morning. You just don't know what hurricane it might inadvertently conjure, or just a slight drizzle. The butterfly effect reminds us that we live in a world of profound interconnectedness and an inherent unpredictability. It's a humbling thought, suggesting that while we can influence events, absolute control or perfect foresight over complex systems remains a tantalizing yet elusive dream. Is it real? So after all this, the million-dollar question, is the butterfly effect real? The short answer is yes, absolutely. As a principle of chaos theory, the idea of sensitive dependence on initial conditions in nonlinear chaotic systems is definitely real and well established in scientific fields like meteorology, fluid dynamics, and cosmology. However, and this is crucial, it's not real in the way Hollywood often portrays it. A single butterfly flapping its wings does not directly cause a tornado in a cause and effect linear domino chain kind of way. It's not about deterministic prediction based on one tiny event. Instead, that butterfly's wing flap represents an immeasurable, infinitesimal permutation in the atmosphere. It's one of countless, unknowable tiny variables that make it impossible for us to ever perfectly know the initial state of the weather system. Because we can't know that state perfectly, we can't predict its long-term future with absolute certainty. Any tiny, unmeasured difference, a butterfly, a dust mote, a rounding error in a computer model, will over time lead to a completely different outcome than if that difference hadn't existed. It's less about the butterfly being the cause of the tornado, and more about the butterfly illustrating the impossibility of perfect prediction in a chaotic system. It highlights the inherent limits on our ability to forecast the future of complex systems. So while you don't need to feel personally responsible for a hurricane every time you swat a mosquito, the underlying mathematical and scientific principle that inspired the metaphor is indeed a fundamental aspect of how our universe operates. Small things can, and do, produce large, unpredictable consequences. It's an elegant, sometimes frustrating, and utterly fascinating truth about the universe we inhabit. And that, my friends, is the beautiful, chaotic reality of the butterfly effect. From a professor's accidental rounding error to Hollywood's most dramatic time travel scenarios, the butterfly effect captures our imagination because it speaks to a profound truth. Our world is not a perfectly ordered machine. It's a dynamic, interconnected dance where even the tiniest step can alter the entire choreography. It's an idea that reminds us that while we can't control everything, every action, every choice, no matter how small, becomes part of that vast, unpredictable tapestry. So go forth, make your tiny changes, flap your metaphorical wings, and see what wonderful or wildly unexpected breezes you create. If you found this dive into chaos theory and fluttering wings as fascinating as we did, please do us a huge favor. Hit that like button, subscribe to What Is for more explorations into the wonderfully weird, and don't forget to ring that notification bell so you never miss another deep dive. And in the comments below, let us know what tiny decision you made that ended up having a huge impact on your life. We'd love to hear your personal butterfly effect stories. Thanks for watching, and we'll see you next time. Hello cosmic adventurers, and welcome back to What Is, the channel where we try to demystify the universe one monumental question at a time. Today we're plunging into one of the most profound and perplexing mysteries of modern science, a riddle wrapped in an enigma, cloaked in, well, darkness. We're talking, of course, about dark matter. It's a term you probably heard, whispered in documentaries, headline articles, or perhaps while overhearing a particularly intense conversation at a science museum. But what is dark matter? Is it a cosmic boogeyman, an invisible space monster, or just physics' way of saying we've found something really weird and we need a cool name for it? Strap in because we're about to explore the invisible scaffolding of the universe, trace the origins of a revolutionary theory, marvel at the ingenious ways scientists are trying to prove its existence, and peer into the future that might just redefine everything we thought we knew about reality. So let's start with the big question, the one that kicks off every episode. What is dark matter? At its simplest, dark matter is the universe's invisible majority. It's a hypothetical form of matter that, unlike the stuff you, me, and everything you can see are made of, doesn't interact with light or other forms of electromagnetic radiation. That means it doesn't absorb, reflect, or emit light. It's utterly, perfectly, magnificently transparent. And because light is how we see everything in the universe, from distant galaxies to the dust motes dancing in a sunbeam, not interacting with light makes dark matter incredibly difficult to detect directly. It's essentially invisible. Now, before you go thinking it's some kind of cosmic ninja, let's be clear about what dark really means here. It doesn't mean literally dark in color, like a black hole. It means it's electromagnetically dark. It just doesn't play nicely with photons. It doesn't glow, it doesn't shimmer, it doesn't even cast a shadow when you see it. It's the ultimate wallflower at the cosmic dance, present but utterly unnoticeable through conventional means. However, just because it doesn't interact with light doesn't mean it doesn't interact at all. We believe it does interact through gravity. And it's this gravitational influence, this invisible hand tugging at the luminous matter we can see, that gave us the first hint that something was amiss in our cosmic accounting books. We can't see it, but we can see its effects. It's like hearing a strange rustling in the bushes. You can't see the creature, but you know something's there because the leaves are moving. Dark matter is the creature rustling the cosmic leaves. For decades, the standard model of cosmology, what we call the lambda CDM model, has dictated that visible, or baryonic matter, everything from stardust to superstars, makes up only about 5% of the universe's total mass energy content. About 68% is taken up by dark energy, an even more mysterious force driving the accelerating expansion of the universe. And the remaining 27%? That's our elusive friend, dark matter. Think about that. Everything you've ever seen, touched, or even dreamed of is just a tiny fraction of what's truly out there. Dark matter is the silent, unseen scaffolding upon which the visible universe hangs. But how did we even come up with such a wild idea? Surely, scientists didn't just wake up one morning and say, you know what? Let's invent an invisible substance to explain things. Well, not quite. The origin of dark matter theory is a story of unexpected observations, stubborn data, a dash of brilliant, if sometimes cantankerous, scientific intuition. Our story begins in the 1930s with a Swiss astronomer named Fritz Zwicky. Now, Zwicky was a character. He was known for his brilliant mind, his sharp wit, and his equally sharp tongue. He famously called his colleagues spherical bastards, claiming they were only bastards no matter which way you looked at them. Not exactly a team player, but undeniably a visionary. Zwicky was observing the Comet Cluster, a massive collection of thousands of galaxies, about 300 million light years away. He was trying to measure the velocities of these galaxies, how fast they were moving. He used the Doppler effect, observing how much light from distant galaxies was either red-shifted, moving away, or blue-shifted, moving towards us, to calculate their speeds. What he found was baffling. The galaxies in the Comet cluster were moving far too fast to remain bound together by gravitational pull of the visible matter alone. According to his calculations, the cluster should have flown apart eons ago. It was like watching a carousel spinning so fast that all the horses should have been flung into the next county, yet somehow they remained perfectly attached. There had to be an immense amount of unseen mass providing the extra gravitational glue to hold the cluster together. Zwicky estimated that there must be about 400 times more mass than what he could account for with the visible galaxies. He coined the term Dunkel Materia, or dark matter, to describe this missing mass. His findings, while intriguing, were largely ignored for decades. Perhaps it was his abrasive personality, or perhaps the idea was just too radical for the time. But the universe, it turns out, is a very stubborn place, and inconvenient truths have a habit of resurfacing. Fast forward to the 1970s, and enter another brilliant astronomer, Vera Rubin. Unlike Zwicky, Rubin was meticulous, patient, and less prone to calling people spherical bastards. She and her colleague Kent Ford were studying the rotational curves of spiral galaxies, specifically the Andromeda Galaxy. Imagine our solar system. Mercury orbits the Sun faster than Earth, which orbits faster than Jupiter, and so on. This is because the vast majority of the mass in our solar system is concentrated at the center, in the Sun. Planets further out experience less gravitational pull and thus move slower. This is how we'd expect stars in a galaxy to behave too. We'd expect stars closer to the galactic center to orbit faster, and stars further out, where less visible mass is contained within their orbit, to slow down. But Vera Rubin found something astonishingly different. When she plotted the orbital speeds of stars against their distance from the galactic center, she expected to see speeds drop off significantly at the outer edges of the galaxy. Instead, she found that speeds remained stubbornly, almost infuriatingly flat. Stars far out from the galactic center were moving just as fast, or even faster, than stars close in. It was like watching a merry-go-round where the horses on the outer edge were spinning at the same speeds as the horses in the center. Which, if you know anything about physics, means that the outer horses should have been flung off into space due to centripetal forces. But they weren't. They were staying put. The only explanation was there must be a huge, invisible halo of mass surrounding the galaxy, extending far beyond the visible stars, providing the extra gravitational pull needed to keep those outer stars in their rapid orbits. Rubin's work provided compelling, undeniable evidence for the existence of this unseen mass. Her observations, confirmed through countless studies of other galaxies, brought Zwicky's dark matter theory from the fringes of eccentricity right into the scientific mainstream. It was no longer just a weird idea. It was a necessary component to make the universe behave according to the laws of physics as we understood them. So the theory was born out of gravitational anomalies. But how has it developed since then? And what further proof, or at least what overwhelming evidence, have we gathered? The development of dark matter theory has been the story of increasingly sophisticated telescopic observations, cosmic detective work, and some truly mind-bending physics. One of the most powerful tools in this arsenal has been the study of cosmic microwave background, or CMB. The CMB is the afterglow of the Big Bang, the oldest light in the universe. It's a snapshot of the universe when it was just 380,000 years old, a mere baby in cosmic terms. By meticulously mapping tiny temperature fluctuations in this background radiation, missions like COBE, WMAP, and the Planck satellite have given us an incredibly precise cosmic census. And what did that census reveal? That dark matter isn't just a local galactic quirk. It's a fundamental constituent of the entire universe. Those tiny fluctuations, the seeds of all future cosmic structures, could only have formed and evolved into the galaxies and galaxy clusters we see today if dark matter was present in precisely the quantities we now describe. Without it, the universe would look very different, much smoother, and far less interesting. Another powerful piece of evidence comes from the phenomenon known as gravitational lensing. Einstein's theory of general relativity tells us that massive objects warp the fabric of space-time, and light, following these warps, appears to bend around them. This is gravitational lensing. When we observe distant galaxies through closer, massive galaxy clusters, the light from background galaxies gets distorted, stretched, or even multiplied into multiple images, just like looking through a distorted glass. By carefully analyzing these lensing effects, astronomers can map the distribution of mass in the foreground cluster. Time and time again, what they find is that the mass distribution inferred from the lensing far exceeds the mass visible in the stars and gas. The lens is much heavier than it appears. This invisible mass, once again, aligns perfectly with the predictions of dark matter. It's like seeing tire tracks in the mud, but no car. You know something heavy passed through, even though it's invisible to you. Perhaps the most compelling smoking gun evidence for dark matter comes from a cosmic collision known as the Bullet Cluster. This is a truly spectacular event. Two galaxy clusters that have smashed right through each other and kept going. When scientists studied the Bullet Cluster, they made a fascinating discovery. The hot gas, which makes up most of the visible mass in the cluster, has been slowed down and heated by friction during the collision, creating a distinct bullet-shaped shockwave. But the overall mass is mapped by gravitational lensing and has sailed right through the collision largely unaffected. This is critical. If dark matter was just ordinary matter that wasn't shining, it would have behaved like the hot gas, slowing down and interacting. But it didn't. It passed right through itself and the ordinary matter, almost as if it wasn't there. This provided direct evidence that dark matter was not just dark gas or dark dust, it was something fundamentally different. Something that interacts primarily through gravity, but hardly at all through the strong, weak, or electromagnetic forces that govern ordinary matter. It's the ultimate cosmic ghost, passing through everything. So if dark matter is not visible matter, what is it? This is where the theoretical physicists step up. Armed with chalkboards, supercomputers, and an endless supply of caffeine. Over the years, many candidates have been proposed, some more exotic than others. Early theories suggested that dark matter might be composed of machos, massive astrophysical compact halo objects. These would be things like black holes, neutron stars, brown dwarfs, that's a failed star, or white dwarfs. Essentially very dim or dark astronomical bodies made of ordinary matter. However, extensive surveys using gravitational microlensing, looking for slight brightening of background stars as machos pass in front of them, have largely ruled out machos as accounting for a significant portion of dark matter. There simply aren't enough of them, and their existence would have other observable effects that we don't see. This leaves us with the more exotic non-baryonic candidates. The leading contender for decades has been WIMPs, weakly interacting massive particles. WIMPs are hypothetical particles that would be much heavier than a proton, interact via the weak nuclear force and gravity, but not electromagnetically or strongly. They would be slow-moving or cold, which fits with the formation of large-scale structures we observe. Many particle physics theories, like supersymmetry, naturally predict the existence of such particles. Imagine a whole zoo of particles we haven't discovered yet, all around us, passing right through us all the time. It's humbling, if not a little creepy. Other candidates include axions, which are much lighter than WIMPs and were originally proposed to solve a different problem in particle physics, but could also contribute to dark matter. Or sterile neutrinos, which could be a type of neutrino that interacts even less than the already famous elusive regular neutrinos. The list is long, and frankly, some of these particles sound like they were invented by a particularly creative Dungeons & Dragons dungeon master. So with all this compelling indirect evidence, have we found any direct proof of dark matter's existence? And if not, what are we doing to find it? The answer to the first question is, frustratingly, no, not yet. We have no definitive, unambiguous direct detection of dark matter particles. But that doesn't mean scientists aren't trying, and the effort involved is monumental. Imagine trying to catch a ghost made of, say, silence. That's essentially the challenge. Because dark matter interacts so weakly, detecting it requires extreme sensitivity and isolation. Scientists have built huge, elaborate experiments deep underground, shielded from cosmic rays and all other known particles, hoping to catch a rare, fleeting interaction between a dark matter particle and an atomic nucleus. These underground labs, located in abandoned mines or specially dug caverns, has detectors filled with supercooled liquefied gases, like xenon or argon. The idea is that if a WIMP, for instance, passes through the detector and occasionally collides with an atomic nucleus, it would cause a tiny recoil, producing a faint flash of light or a whisper of ionization. It's like trying to hear a feather drop in a completely soundproofed room. Experiments like Xenon, Lux, LZ, and Panda X, and many others, are pushing the boundaries of detection technology, searching for these incredibly rare events. So far, they've set impressive limits on what dark matter isn't, ruling out certain masses and interaction strengths, but no definitive ping has sounded the alarm. Another avenue of direct detection involves looking for the byproducts of dark matter annihilation. If WIMPs are their own antiparticles, they might occasionally collide and annihilate, producing gamma rays or other particles we can detect. Space telescopes like the Fermi Gamma Ray Space Telescope scan the cosmos for these telltale signatures, particularly from regions rich in dark matter, like the galactic center. Again, hints have emerged, but nothing conclusive enough to declare victory. And then there's the possibility that our particle accelerators, like the Large Hadron Collider at CERN, could create dark matter particles in high energy collisions. If supersymmetry is correct, for example, then the supersymmetric partners of known particles, including potential WIMPs, might be detectable. The LHC has proved a powerful tool for discovering new particles, including the Higgs Boson, but dark matter particles have so far remained frustratingly out of reach in these terrestrial experiments. The incredible thing is that despite decades of searching, despite billions of dollars, and countless hours of brilliant scientific minds, we've found nothing definitive. And paradoxically, that lack of direct detection is almost as interesting as the discovery would be. It means dark matter is even more elusive than we thought, forcing theoretical physicists back to their chalkboards to revise models and propose even stranger, more weakly interacting particles. The universe, it seems, enjoys a good game of hide and seek. So what does the future hold for the quest for dark matter? The search certainly isn't slowing down. Next generation direct detection experiments are being designed, aiming for even greater sensitivity. The LHC and future particle accelerators will continue to probe higher energies, hoping to unlock new realms of physics where dark matter particles might reside. New telescopes and observatories, both on Earth and in space, will continue to map the universe with increasing precision, refining our understanding of dark matter's distribution and gravitational effects. There's also a category of alternative theories that challenge the very premise of dark matter. The most prominent of these is modified Newtonian dynamics, or MOND. MOND proposes that at very low accelerations, like those experienced by stars in the outer reaches of galaxies, gravity behaves differently than predicted by Newton and Einstein. Instead of inventing a new particle, MOND modifies the laws of gravity themselves. While MOND can explain why a galaxy rotation curves remarkably well in some cases, it struggles to explain other phenomena, like gravitational lensing in galaxy clusters or the bullet cluster, and particularly the cosmic microwave background. The prevailing scientific consensus still favors dark matter because it offers a more consistent explanation for a wider range of cosmological observations. But the fact that MOND exists and has its proponents shows that the scientific community is open to truly radical solutions if the evidence eventually demands it. Ultimately, The discovery of dark matter, or a comprehensive understanding of what it is, would mark a monumental shift in our understanding of the universe. It would not only reveal a huge, previously unknown component of reality, but could also lead to new physics beyond the standard model of particle physics. It could connect the largest structures in the cosmos with the smallest particles. It might even offer clues about the early universe, the nature of space-time, or the very fabric of existence. Imagine a universe where 95% of everything is fundamentally different from the 5% we experience. That's the universe we're trying to understand. The quest for dark matter is a testament to human curiosity, perseverance, and the relentless drive to uncover the deepest secrets of reality, even when those secrets are incredibly, frustratingly dark. Whether it's a WIMP, an axion, a sterile neutrino, or something we haven't even conceived of yet, one thing is certain: dark matter is out there. It's tugging at the stars, shaping the galaxies, and forming the invisible backbone of the cosmos. And someday, perhaps with a flash of light in a deep underground lab, or a subtle anomaly in a particle collider, or a revolutionary insight from a new theory, we might just finally drag this cosmic ghost into the light. And when we do, our universe will never look the same again. So what do you think dark matter is? Do you have a favorite hypothetical particle? Or do you think there's a different explanation altogether? Let us know in the comments below. If you enjoyed this cosmic deep dive, please remember to hit that like button, share this video with your fellow curious minds, and subscribe to What Is for more explorations into the universe's most mind-bending questions. And don't forget to ring that notification bell so you don't miss our next adventure. Thanks for watching, and as always, keep wondering. See you next time.